resting potential, there is a balanced amount of sodium and potassium ions inside and outside of the cell, meaning there are more sodium ions outside and more potassium ions inside. The charge is more negative inside the axon, so voltage, which is a difference of charge across 2 points of a membrane, is negative 70 millivolts. When a stimulus comes, the sodium-gated channels open. The sodium ions then move into the cell until the cell reaches the threshold of negative 50 millivolts. Then all the channels open and more sodium ions enter the cell. When the threshold is passed, the cell is depolarized and an action potential is now generated. In order for the cell to fire out another action potential, the resting potential needs to be restored. First, the voltage-gated sodium channels become inactivated and close, which stops the flow of sodium ions. Then, voltage-gated potassium channels open, allowing potassium ions to follow its concentration gradient out of the cell. This causes the voltage across the membrane to fall. The cell is now hyperpolarized. First, the potassium channels and sodium channels close. Then the cell uses the sodium-potassium pump to re-establish the resting potential by pumping out sodium and to pump in potassium. In order to accomplish this, the pump uses energy in the form of ATP. 3 sodium ions bind to the pump. ATP binds to the pump, giving it a phosphate. When the phosphate binds to the pump changes shape, which causes the sodium ions to get pushed out. Then 2 potassium ions bind to the pump. Phosphate leaves the pump, which changes the shape of the pump again, causing potassium ions to get pushed out.
Agitoxin is a neurotoxin, and this is its structure. And it's found in scorpion venom. And agitoxin role is to allow various protein complexes to be enacted. And it does this by blocking the Shaker K+ channel by sitting on the channel and preventing its opening by movement of different side chains, allowing various protein complexes to be enacted. And it undergoes structural changes following the induced fit model. And agitoxin is central to the understanding of potassium channels, since potassium channels are implicated in several human pathologies like asthma, T-cell mediated immune diseases, such as multiple sclerosis, type 1 diabetes, and hypertension. As illustrated, the scorpion toxins specific for potassium have been vital to enormous amounts of research, resulting in the identification and classification of new channel types and families, as well as the creation of new structural models pertaining to the gating and binding of numerous ligands. And bioengineered scorpion toxins have been monumental to the evolution of channel science and serve as templates for experimental molecular therapeutics.